Good evening, everyone. Welcome to the official first meeting of Cape Centre for 2021. For those that know how we normally operate, we don't have a meeting in January, and we very normally do have a meeting in February. But as you all know, we normally meet on the last or on the fourth Wednesday of a month. Unfortunately, the meeting of last week had to be pushed into this month, which puts us in a different or advantageous place. We're probably going to have 2 meetings in March. But tonight's speaker is Jonathan Schock, and Jonathan has joined early, and we've been listening to what Jonathan's been up to for the year so far and keeping himself busy. Jonathan is from Gardens, and as he was explaining to us, he's very actively busy getting into astrophotography. And he's looking for some guidance from some of the gurus and experts in our group. And I see Paul Heeman here. Paul, you're one of the gurus. So maybe Jonathan can have a couple of words with you later. He's looking for some literal and physical guidance with regards to a mount. But before we start, let me first tell you guys a little bit more about Jonathan, and let me just get my paperwork out so that I can sound all professional. So Jonathan is a senior lecturer at the University of Cape Town, and he's in the Department of Maths and Applied Mathematics. Jonathan still completed his PhD in the UK in high energy theoretical physics. He completed a postdoctoral in China, Spain, and Germany before coming to UCT in 2013. His research interests, his research interest covers theoretical physics, artificial intelligence, neuroscience, and data analysis in biology. And he spends a good deal of his time supervising students while or when he's not teaching. And he's a keen photographer, and he's slowly dipping his toes into the waters of astrophotography, but knows that this is the first tentative step into a very long journey. Jonathan, very well put, but I fully agree with that. And I think there's a lot of people here that says that that's absolutely a bottomless pit once you get involved with that. Jonathan, what I would like to do is hand over to you. So if you just give me a second, I'm going to make you co-host, and then you can carry on. So please just give you a second here.
Sure.
There you go, Jonathan. I've given you co-host, and I'm also putting the spotlight on you. So
fantastic.
There you go. Over to you.
Let me see. Can you see this okay?
What are some problems with RL?
oh dear. I've given the game away. Hang on. There we go. How's that?
Perfect. You've got the floor.
Perfect. Sure. Thank you very much, Marius. And thank you also to Ketchel for getting me involved with this. I'm extremely grateful. It's lovely to meet this community. As Marius says, I am kind of dipping my toes into the world of astrophotography and would be very keen to get some advice later on, so that would be wonderful. So I hope it's going to be okay that I'm not going to be talking much at all about astronomy. There may be a little hint at the end, but most of this is going to be about artificial intelligence, and in particular an area of artificial intelligence called reinforcement learning, which is something that I find one of the most interesting developments over the last few years, and sort of gives us an insight into how we might be able to take ideas from human and animal-like behavior and utilize them to get machines to behave in interesting ways, in creative ways even. And creativity maybe isn't something that we think about often in terms of computers, in terms of machines, but I'll talk about some examples where we've actually seen real creativity come out of machine learning. So what I want to talk about first is simply what is artificial intelligence, but really to answer that question. So I'm having to move some things around here so I can read what I've got here. There we go. So to think about artificial intelligence, we might want to think about what is intelligence in general. And in fact, defining intelligence in humans is not only difficult, but sometimes dangerous. And so we want to be a little bit careful with that. So I found a couple of definitions here of artificial intelligence, neither of which I like very much, but I wanted to read them out because I think it explains why pinning down what artificial intelligence is sort of interesting and difficult. So it says here that artificial intelligence is the ability of a digital computer or computer-controlled robot to perform tasks commonly associated with intelligent beings. And maybe that's true, but there are plenty of behaviors and tasks that intelligent beings do that one wouldn't think of as intelligent themselves. And there's a lot of things that we want to get artificial intelligence machines to do, which aren't actually things that humans do or animals do. And then colloquially, the term artificial intelligence is often used to describe machines or computers that mimic cognitive functions that humans associate with the human mind, such as learning or problem solving. And again, this is certainly sometimes true, and it's clearly not always true. So let's look at some examples. I guess the thing that we might want to do is, can we ask a computer a question and can the computer answer it? So you could ask a computer a question like, what is this image? You could give it a picture of a dog or a cat or a person and ask it to identify the image or to describe the image in some way. You could ask a computer to calculate the sign, the trigonometric function of some number. You could ask it what the weather will be like on Tuesday, and that may be that you wanted to do that by doing some simulation of weather dynamics or maybe searching on websites. You might ask a computer how it's feeling today. These are all questions that you could think of asking a human, and you would think that there is some sort of intelligence going on if they can answer it, and indeed there's some sort of intelligence going on if a computer can answer these questions. The what is sign of 3.2 doesn't really seem like intelligent behavior because there's no conditional thing going on there. There's no sort of if statement. The computer is simply following a set of rules and coming up with the answer in the end. So I guess the question that you might ask is, when the computer is doing these things, is it having to make some decisions along the way? Is it coming to some junction and making a decision? Well, the situation is like this, and so I go down this route. Otherwise, I go down this route. So one could ask, does an if statement make something artificial intelligence? And I think that's part of the way, but clearly there's a lot more to it than that. So in terms of machine learning, what we really want to ask is, given a set of data, can a computer learn to make generalizations and classifications based on this data? And so data can come in many different forms, and data might be something like an image. So it might be that you give a computer data in the form of lots of images of cats and dogs, and you wanted to be able to recognize in the future what is a cat and what is a dog. And so in that case, you would label your data. This is a picture of a dog. This is a picture of a cat. It might be that you give a computer pictures of cats and dogs, and you say to it, can you find clusters? Can you find clusters here whereby you see that there is a category, you don't know what it's called, we know that it's called cats, but you see that there is some category of objects which is somehow alike and another category which is somehow alike, and we can then tell it, these are cats and these are dogs. Or indeed, can you do something even more powerful? Could I give it pictures of cats and say, can you generate for me a new picture of a cat? That would certainly seem to be intelligent behavior. If you give an artist pictures of cats, then it will be able, the artist will be able to draw a picture of a cat which has never existed, but everybody will recognize as a cat. So there the question is, can it generate more somehow similar data? So we can ask the question, what is not machine learning? So in general, if we have a set of handwritten rules, so that is to say we have a computer which is simply processing information by a set of rules, which go like a flowchart. So there's no condition on the rules. It's simply running through the rules. And this isn't machine learning because it's not learning the rules themselves from data. And we'll see in a moment what I mean by this. But essentially in machine learning, what we want is that the rules themselves are decided on by the computer, and that's based on the input data, the data that you're giving it to learn. Move this down again. Sorry, my mouse disappears halfway through here. So we sort of go from one extreme to another. And this gives us something which is very powerful. So we could start on the left here with a set of rules which is very easy to understand. And so that might be a set of rules whereby you tell the computer something, you give the computer some data set, and the set of rules are if you see some whiskers, and if you see a nose, and if you see 4 legs, then it's probably a cat. So if you see the input is something, then do something else. So that is to say, if you tick all the boxes, then the output should be cat. And in that case, each rule is handwritten. So you code up something in your programming language, which is a whisker detector, and you code something up, which is a paw detector and a nose detector. And each one of those is handwritten. And you can certainly do that, but it turns out that's not all that powerful. Sorry, I'm having to shift things around on the screen all the time here. It's not necessarily particularly powerful because as the programmer, you need to hard code everything in. And so you need to think of all the possibilities, and that's very complicated. So something which is more abstract is that you can define these by mathematical functions, and I'm not going to go into the details of that. But essentially what that would do is to take your image and figure out for itself what are the interesting features. So you wouldn't have to say this is a whisker and this is a paw. The computer somehow, by seeing lots and lots of images, will say, now I know that there is a feature which looks like some sort of set of straight lines, and this is a feature which I'm going to associate with cats. So you haven't told it anything about that rule. It has figured out that rule for itself. And so this is this sort of meta idea that rather than teaching the rules, you get the computer to figure out what the rules are. And that's really the power of machine learning. So the rules for the rules themselves are handwritten. So you say, I want you to find features. So I want you to find features in this data which are somehow give you clues to whether this is a cat or a dog. And this is much more powerful. And essentially over time, this is what's happened. We've gone from hard-coded rules where we tell the computer what features to look for to much more powerful systems where we give the computer rules to define rules for itself. Okay? And kind of the idea would be, in terms of our behavior, here is an exact recipe for lasagna. Can you cook a lasagna? And all you have to do is to follow the rules, and indeed you create something in the end. You create a lasagna. But something more powerful would be, here's a set of popular foods. Can you look at these popular foods and figure out what are the types of ingredients that go well together? What are the rules that make for good food? And then taking those rules, abstracting them, you can then design some new and tasty food, which is likely also to be popular. So here I have the sort of big picture of artificial intelligence and machine learning. And the first thing you might see here is that within the set of artificial intelligence, there is a subset, there is a set of ideas, concepts, algorithms, which are machine learning. And this sort of hints to the fact that maybe there's a set of things which are artificial intelligence, but which are not machine learning. And it's true, there are ideas of formal logic and expert systems. I'm not going to talk about those at all today. But within the world of machine learning, there are kind of 3 broad areas. The first one is supervised learning. And in supervised learning, the idea is that you give some sort of labeled data set. So the labeled data set might be something like, here's a set of pictures of galaxies. And I'm going to give you the labels of those galaxies. So here is a barred spiral galaxy, here is an elliptical galaxy, here is a globular cluster, whatever it might be. So you give the computer thousands and thousands of images, each of them labeled, and the computer, through the algorithms that you teach it, learns to find features. So you don't teach it anything about bars or spirals or ellipses or anything like this. But the computer learns to spot features and associate them with a particular category. So it realizes that there is some feature which is common to barred spiral galaxies. And then when you give it a new image of a barred spiral galaxy, it's going to say, this is one of those because I've realized that there is something in common with the previous examples. Down on the bottom left here, you see a much, much simpler example. So we've got a set of scattered data where we've got the x-axis and the y-axis. And the question that you might ask there is, okay, so given this data, the blue points there, if I'm to give you a new value on the x-axis, can you predict what the y value would be? And indeed, thereby fitting a straight line, the red line, which is somehow the line of best fit through this data, you are able to make a prediction about some x value which you've never seen before. So both of these are supervised learning because in both cases you've given labeled data. So you've said, this is a particular type of galaxy, or you've said, for the data that I have here, this is the y value associated with this x value. Now can you extrapolate? On the right-hand side, we have unsupervised learning. So in unsupervised learning, we don't give any labels. So for instance, I might give a data set like the one on the bottom right there, where you've got a load of dots. And the aim of the computer is going to be to realize that there are 3 clusters here. So if you gave this data, you wouldn't give them as red, green, and blue. You would simply give them as positions in this 2-dimensional plane. And you would say, can you find clusters in this data? And there are various means of doing that. So there's something called k-means clustering, which is a fairly intuitive algorithm. But the important point here is that you haven't labeled what are the green, what are the red, what are the blue. You simply say to the computer, I want you to find clusters within this data. So in terms of the galaxies there, it might be that you don't label, barred and elliptical and all of the other labels for the galaxies. You just give it pictures of galaxies and say, hey, can you find interesting clusters here? Can you say these galaxies in some sense are all the same and these galaxies in some sense are all the same? And then in the top right, we've got something called a generative adversarial network. And what I said before was essentially, if I give you a set of pictures, can you come up with a new picture, which in some sense is similar to the ones that I've already given you? So these pictures at the top right, this is as part of something called CelebGAN. So these all look like celebrities, but in fact, none of these people exist. These are images that have been generated by a computer which has been trained on images of celebrities in the past, and it has learned through a very clever algorithm of essentially trying to trick another computer. It's learned to produce these images of that look like celebrities. And then we have reinforcement learning, and reinforcement learning is what I'm going to focus on for the rest of the talk. And then we've sort of got this circle in the middle of deep learning, which is the application of so-called neural networks to each of these fields of supervised, unsupervised, and reinforcement learning. And the point is that neural networks allow you to do much more powerful things than you could do otherwise. So rather than just fitting a straight line through some points, you can classify images of galaxies. Rather than just finding clusters in data, you can generate images of new instances based on the data set. So a question that I have for all of you is, why are you here? Why are you here listening to me talk at the moment? And this isn't simply for you to think of existential questions at this time of the evening. It's actually because the reason you are here is because I presume you made some decision. You decided in some sense that being here would be valuable to you, either in terms of being part of this community or in terms of maybe learning something interesting and being able to use that information in the rest of your lives, either because you might end up wanting to work in reinforcement learning or because it becomes an interesting topic of conversation for some other time. But the point is that the way we move through the world is by making decisions based on what we think has value. And that might sound a little bit utilitarian, But we take decisions all the time, and we have to decide, do I want to do this or do I want to do that? And in some sense, we think that the things that we do are the things that have value, and that may be intrinsic value based on, getting nutrition. I eat because it gives me some sort of nutritional reward. Or it might be that I come to a talk because I believe that the information in the talk may lead me to somewhere else, which might lead me to a job, which might lead me to get more money, which eventually leads to being able to buy more food. So reinforcement learning is actually exactly about this. It's about getting machines to learn how to move through some sort of environment based on the machines figuring out which states have value. So the things that we're going to need to think about are, what are the states of a system? So the aim is going to be to get an agent, a computer, a machine, to move effectively through some system to solve some task. I haven't really told you much about what reinforcement learning is yet, but we'll get onto that. So we need to think about a set of states that you or the machine can be in. So the environment can be in some state. Whether it's raining or not, where you are, who won the election, all of these are states of the environment or states of yourself. There's a set of actions that you can take, and they depend on the state. Sometimes you'll be able to jump up and down, and sometimes you'll be able to move the steering wheel of your car. So the actions that you can take are dependent on the state that you're in. Often, you will be able to move your left hand, but maybe not always. And then there are rewards that you get from being in certain states. You might get food, you might get comfort, you might get reproduction. And these are all sort of very basic evolutionary rewards. But those, in some sense, are the things that you are trying to do in order to survive or in order to prolong your gene line or whatever it may be. So through evolution, we've got these set of defined rewards: food and comfort and reproduction. So then the question might be, what's your policy, conscious or subconscious, for getting the most reward possible? The policy says, given that I'm in some state, and we're going to call it the state S, what's the action A that I should take? That's what a policy is. The policy is, given I'm in some state, what should I do? So this is the fundamental framework of reinforcement learning. So we have a brain here, and we're going to call the brain the agent or the machine, the computer. And the agent gets some information from its environment. It gets, just under this number 1 here, it gets S subscript T, which is the state of the environment at time T. It also might get some reward from the environment at time T. It might get some food, or it might get some other signal, which is a reward. And based on its policy, it says, okay, well, now I want to take action A at time T. That action then feeds back to the environment, and the environment changes in some way. It might be that you have moved the car along a little bit, or it might be that you have made dinner, or whatever it is. The environment is now in a different state. The world is in the state of dinner having been made or the car having moved. The environment now feeds back to the agent. So we've now got state ST+1 and a reward RT+1, and these feed back. And the point is that this just keeps going and going and going. But what is it that we're actually trying to do? Well, we'll see in a moment that what we're trying to do is to increase the total reward over time. So the environment reacts to an action, and this may be stochastic. And by stochastic, I mean sort of non-deterministic, in that sometimes the environment might do one thing and sometimes it might do another. It'll move into a new state and it'll give back some reward R. So here we have a fundamental idea which is associated with Pavlov, but is used very directly within reinforcement learning. And it's what he called psychic secretion. And in fact, psychic secretion was the name he gave to the salivation of the dog when it heard the bell. So the idea here is that food is the reward. Food is the thing that the dog actually wants. But by associating the bell with the food, somehow the dog realizes that when it hears the bell, there is some value. And what we're going to want to do in reinforcement learning is to have a set of rewards, which are the things that we really want to get, or we want the agent to get. And we want to associate values with states. There's no intrinsic reward in the ringing of the bell, but there is value in it because we have associated it with a future state, which is the food. So here's an example. Here we have states in blue, actions in green, and terminal states here are in yellow, which is sort of the end point here. So we might start off, we're in bed and we need food. We might do nothing, in which case, of course, we'll remain in bed and need food. We might get up, in which case we're standing. Then we have a few different options. We might go to the kitchen. If we're in the kitchen, we might make breakfast, or we might browse Twitter. And if we browse Twitter, well, then we're still hungry. If we make breakfast, breakfast is made. As long as we eat the breakfast, then we're going to end up in a state where we're satisfied. So at each point here, we might have some choices to what we can do. We have a choice of action. And remember, that choice of action is the policy. So if we wanted to move through the world in this way, well, we would want to find a policy which takes us from in bed and need food to the state of satisfied most efficiently. So we can think about assigning some numerical reward with these states. So the satisfied state has a reward of +1, and the -1 state has a reward of -1. The hungry state has a reward of -1. And of course, we want to end up with the biggest reward possible at the end of the day. We can then associate value with the other states. So the point is that because we know that given the best policy, we can start off with in bed and need food, and from there, we can end up in the state satisfied, we can say that actually that first state has a value of +1, because we know it can lead us to the satisfied state. Similarly, when we're standing, we know it can lead us to the satisfied state. So that's also got a value of +1. However, we see that we could go round and round and round and round and do nothing and do nothing and do nothing, and we'll remain in bed, and it'll take a long time to get to the satisfied state. So we can include something called discounting. And discounting says, well, I know that I can get from, for instance, the breakfast made state to the satisfied state by eating breakfast, but that's one step away. So we're going to associate a value with the breakfast made state a little bit less. There's going to be some discount because it takes one more step to get to the state where there's actually a reward. And similarly, the in bed and need food state has a slightly lower value because, well, it's going to be a little while into the future that we get to the state of actually being satisfied. And so what we really want to do here is to move through states which have the highest value possible, which means that we want to get to the satisfied state as quickly as possible. So then we might also have some non-determinism here. And non-determinism means that, well, we're in bed and we need food. Well, if we get up, well, we might be standing, in which case great, or we might faint, in which case we end up in the hungry state and we're on the floor and we have a reward of -1. If we go to the kitchen, well, we might end up in the kitchen, or it might be that someone's turned the kitchen into a swimming pool, in which case we're still hungry. So this whole thing is actually something called a Markov decision process. And a Markov decision process is really a set of states and actions and rewards whereby we can move through an environment and figure out somehow, using some set of algorithms, and I'm not going to go into the details of the algorithms, but we can figure out what are the values of the states. Because if we can figure out what are the values of states, we can most efficiently get to the highest reward states. So what is reinforcement learning? So reinforcement learning really came about via a connection of two disciplines. One is psychology, the idea of learning through trial and error, and this idea of secondary reinforcers. So the bell in Pavlov's experiment is a secondary reinforcer because it allows us to realize that there is some value in some state, which is then associated with a reward. And an area of computer science called optimal control theory, computer science engineering called optimal control theory, whereby we have things called value functions and dynamic programming, and there's not really learning going on here. But when you put these two together, learning through trial and error and figuring out well-defined values of states, then we end up with reinforcement learning. So really, reinforcement learning is the application of trial and error search through some space to try to solve some problem where the problem has a well-defined reward structure. That is to say, for instance, I might say to you, I want you to learn how to play this computer game. And the reward is going to be to get a high score in the computer game. And what you'll do is to play the computer game, and by trial and error, by moving in certain directions with the controller, you'll find that you get more and more reward. And so you will associate value with the things that you did, with the policy that got you to those high reward states. And that's exactly what we can do with computers. So teaching rules is very hard. So it's much easier when a system can learn for itself. So for instance, in that computer game example, I could tell you in theory exactly how to solve the game. I could say, when you see the screen like this, you must move the button to the right. And then when you see the screen like this, you must move the button up. That would take a long time because there are so many different states that the computer screen could be in. This is going to be really hard to teach all of the rules. What's much easier is if I let you learn for yourself by trial and error. So it might seem that this is sort of part of supervised machine learning, but actually it's not, because we're not instructing the machine what to do. We're giving evaluative feedback. That is to say, we're saying to the computer, hey, you did a good job. You got a high score here. Or no, you did a bad job. You died in the game, or whatever it might be. So we're giving evaluative feedback. So how do we do this? How do we actually get a computer to learn to perform a task? Well, of course, we need to define some environment, and the environment might be something like a computer game, or it might be something like a car, which we want the computer to learn to drive, or it might be a telescope system that we want it to learn to focus. It could be many, many different things. And we need to define a set of rewards. So the reward might be to get the car to move from A to B as quickly as possible. And when it does so effectively, then it gets some reward. It might be that we want it to score well in a game. And then the agent, which is the machine, the computer program, it gets to interact with the environment, and it needs to figure out what are the values of each state. So we tell it the rewards. We say, hey, you get a reward when you get to this state. But it needs to figure out, hey, the states before that allowed me to get to that high reward state, well, there's some value associated with them. And by learning the values of states, it's able to realize the best policy to move through the environment. So in general, the number of states for a system like a computer game, a very simple computer game like Tetris, is incredibly high. So in fact, Tetris has around 10 to the 60 different possible states. There are 10 to the 60 different ways that...
Psychiatry.
Can we just ask everyone to mute their backgrounds, please? Thank you, Jonathan, for the quick second.
Sure. So, even a simple game has a very, very large number of possible states. And it turns out that actually using a sort of lookup table whereby associated with a given state is an associated action actually isn't a very efficient way of doing that. And what we end up using are neural networks. And neural networks are a way of encoding very complex information in far fewer parameters. I'm not going to go into the details of neural networks, but that's how this is often done these days. So let me see if this is going to work. Yes. So here's an example. So this is something called a swing up cart pull. And what we have here is a little controller where we have a cart on a rail, and it can move left and right. And the aim of this is to learn to balance the pole vertically upward. And we don't give it any information about the dynamics. All we say to it is, we want you to figure out what are the correct actions to do in order to balance the pole upright as much as possible. So balancing the pole upright in this case is the reward. We say, okay, every time it's balanced at a certain vertical position, you're going to get a reward of +1. And so what it does to start with is it starts moving randomly because it has no idea what to do. And it finds through trial and error that every now and then it does something which makes the pole go a little bit more vertical. So in this case, it's sort of somehow found that moving backwards and forwards like this keeps it a little bit more vertical. It takes that information and uses that the next time to try again. Sometimes it's going to exploit the information it already knows, and sometimes it's going to explore new types of information. So now at 10 seconds, it's gotten pretty close, and in fact, we'll see on the next one, I think, that it's basically mastered the game within 12.5 seconds. And remember, this is without programming in any of the physics, any of the dynamics of what's going on here at all. So you're going to do it on this one? So not quite, but it's pretty close. So it'll be on the next one. It's mastered the game. And the way that it's done that is to realize that in certain positions, certain states are valuable. So states which are close to the high reward states are valuable, and it's trying to get to those. And then once it's got to those, okay, maybe on the next one, once it's got to those, it can then maneuver into the position where it's actually got the thing to go completely vertically. I don't remember if it's, yeah, so it's going to do one more. And at this point, it really has actually solved this problem. It's entirely through trial and error. No hard-coded rules about gravity or about dynamics have been coded in. And now after 17.5 seconds, it's mastered the game. So computer games are sort of a nice framework whereby they're very clean. We know exactly how they work, and they're very well defined. They're well defined in the sense that what we want to get the computer to do is to get a high score. So the score in this case is the reward. And so what we see here is one of the Atari games. It's called Breakout. And you see here, this is sort of the first few minutes of play. And the aim here is that the paddle at the bottom of the screen is moved about by the agent, by the computer, and it's trying to bounce the ball into the blocks. And as it bounces it into the blocks, it gets more and more points. And again, through trial and error, it starts to realize that in certain states, particular actions are the ones that it should do in order to increase its reward. And after a couple of hours of play, well, it's up to the level of an expert human. It's pretty good at the game. But what's rather interesting is that if you leave a system like this for long enough, if you let it play for long enough, what it's actually going to do is to find ways to solve the game in ways that maybe a human hasn't figured out. So this is after now 240 minutes, 4 hours of gameplay. And it's doing all the things that you would expect an expert to do. But what it realizes is that if it creates a hole in the top left, which it's going to do in just a moment, then it sort of found a shortcut to this game. And this is what you often find is that you might not, as the programmer, have realized that that is a good way to solve this problem. But the computer, through trial and error and very clever algorithms, so all of this is happening through a series of deep neural networks and things called deep Q learning, it realizes that there are better ways to play the game than even a human might have realized. So here we see another example where we have a little simulated robot, if you will, humanoid or biped here. And the aim here, the reward is getting to a certain place. And the feedback then is, the agent has done well if it gets to that place. And all it's done is it's told to figure out the right movements in order to do this. Again, there's no physics programmed into the agent's understanding of the world. It tries over and over again, and it realizes the right actions to take in a given state in order to solve this problem. And sometimes it does it in the way that humans would do it, and sometimes it finds interesting shortcuts. And it can even move around obstacles. Maybe not very elegantly all the time, but it manages to solve the problem. Most of the time. These sorts of things can also be built into self-driving cars. And of course, you don't want to put a car onto the road and just say, learn for yourself through trial and error, because, well, it turns out that errors with cars tend to be fairly costly. But what you can do is to set this up in a simulation and get the computer system, which will be in the car, to learn through trial and error, to learn how to get to reward states, high reward states, by making mistakes along the way and learning from those mistakes. Within manufacturing as well, again, you have a very well-defined environment. So you have an environment where there are certain actions, there are certain states, and there's a well-defined reward. And in this case, the reward might be produce as many cars as you can, or produce them with as much efficiency as possible, produce them with as little waste, whatever it might be. And so again, by slightly changing the actions that the agent, which is controlling the robotic arm in this case, does, it can figure out ways to solve the problem better than a human would be able to, just by trying to think, what's the best way that I think we should do this. So one of the nicest examples, I think, of creative play has been the game of Go. So Go is a game which is sort of similar to chess. It's a two-player game. And in some sense, it looks simpler. There's only one type of piece for each player. One player is the white pieces, one player is the black pieces. And the aim of the game is to capture regions of the board. And what we see here is the World Go champion, actually for many, many years, a Korean by the name of Lee Sedol. And this was about 3 or 4 years ago now. The AlphaGo system, which is a computer system based on reinforcement learning, learned to play Go. And the way that it did that, well, first it was given 100,000 historical games of Go played by humans. And then it played itself over and over and over again, many millions of times. And it learned to associate value with particular states in order to get to the reward, where the reward was simply winning the game. So a competition was set up between AlphaGo and Lee Sedol, and essentially all of the top Go players in the world thought there was no way a computer would be able to beat him. He's just brilliant. He's far surpasses any other Go player. And the point is that even though Go looks simpler, Go is actually a much more complex game than chess. There are far, far more options, and there are far, far more strategies than there are even in chess. It's an astronomical number. In fact, it's even beyond an astronomical number, I guess. And in fact, what happened was that in the very first game, AlphaGo, the system, beat Lee Sedol soundly. And the Go world was kind of horrified by this. You know, suddenly computers were able to do something that we didn't think they would be able to do because this problem seemed simply too hard for a computer. What happened in one of the subsequent games was a famous move called, I think it's move 34. And in move 34, the computer played a move which seemed to be a mistake. And everybody, all the announcers around the world who are televising this competition said, you know, it's okay, you know, computers are fallible and humans still have the upper hand because computers make these really elementary mistakes. And Lee Sedol came back to the board and he looked at it and he realized in that moment that this wasn't a mistake. This was a move that no human would ever make. And in fact, in doing so, it opened up an entirely new set of strategies that humans had never seen. They'd never seen that this was a possible way to play the game. And it was seen as a beautiful and creative move. And if one thinks of creativity as novel behavior or novel things which have value, then this was without a doubt a computer creating something valuable. So we've seen from chess and from Go, computers, although yes, they're much better than humans now, they're actually enhancing the play of humans because now all of the top chess players, they use computer systems to show them new ways to play the game. And the same thing with Go. The same thing with this so-called Dota 2, which is an incredibly complicated, at least for me, game, lots of strategy. It's a very graphically heavy game. And OpenAI was able to beat the world champions at this game. And this was back in 2018. So in fact, I was wondering how I might be able to connect this at all with astronomy, and I put in reinforcement learning astronomy, and it turned out that actually Bruce Bassett supervised a student in 2019 on precisely reinforcement learning for telescope optimization. And essentially this was about scheduling. So the question here is, if you have a telescope which can view certain objects, given particular constraints, the time of the year, the weather, the particular optical conditions, what's the best order to do this in? And in fact, they used reinforcement learning to be able to come up with a schedule which was more optimal. It may not be the optimal because there's a huge space here to search through, but they were able to use it to come up with a schedule which was more efficient for observing objects given all of the different constraints. So, you know, I had to have a little bit of a stretch here to find the relationship between reinforcement learning and astronomy, although clearly there are very, very strong links between machine learning in general, particularly supervised and unsupervised learning and astronomy, but even within the world of reinforcement learning. When you have anything where you have some well-defined environment and some well-defined reward structure, you can use reinforcement learning to solve a task. Of course, what you need to be able to do is to define the reward structure appropriately. Now, there are lots of problems with reinforcement learning, things like transfer learning. So the idea here is, let's say I've got a computer to solve some particular task. it actually turns out that at the moment that you can do that, you can get it to play a game. But now if you give it a different game, it doesn't do that very well. It hasn't really learned anything about some new context. And what we want to be able to do is to get computers to learn in one context and take that information and transfer it to another context. So-called curriculum learning, which is really about learning to perform sequences of actions. So if I want to cook dinner, I don't think about the muscle fibers that I need to move. I think about, the ingredients that I need to put together, and I have sequences of actions that are built up from those microscopic ones from moving particular muscle fibers that build up. And really what I think is, now I need to crack this egg, or now I need to whisk this, or now I need to put this sauce in the pan. And so curriculum learning is really about how do we get a computer to chunk together action sequences so that that now becomes a single action. The so-called long-term credit assignment problem is particularly difficult. So if you have a problem where the rewards are very sparse, so that is to say that way, way, way at the end of the game, you get a reward of +1. What happens throughout the beginning? Well, the answer is that the agent needs to realize that there is value in states because they lead to the reward. But if the reward is a long way off, then it turns out to be really difficult to get the agent to figure out precisely the path through the state space to get to that reward. And so one way to do this is to give an intrinsic reward associated with curiosity. So there's something called curiosity-driven reinforcement learning. And what this means is that, yes, the agent gets reward for, solving the game, but it also gets reward for exploring spaces that it's never seen before, that it has most uncertainty about. So actually including curiosity in these sorts of agents actually turns out to be very powerful. One has to make sure that the agent is solving the problem that you want. So there was an example. So this example of the sort of simulated people or quadrupeds moving around, there was an example where the programmers said, I want this four-legged little robot to get from A to B, and the constraint was that it should have its legs on the ground for as short a time as possible. And what the agent wanted to do was figure out how to get this little four-legged robot to jump or to run in an efficient way. But actually, they let the program run for a while, and what they found was that it found a solution where it flipped onto its back and it shuffled across on its back, so that its legs were actually not on the ground at all. So you have to be very, very careful with exactly how you give it the constraints and exactly what the reward structure is. So there's a couple of places that I would highly recommend if you're interested in learning a little more about reinforcement learning. So I haven't told you about how these algorithms actually work. I'd be very happy to discuss that after. The book by Sutton and Bartow on reinforcement learning, it's for free online. It's an extremely well-written, very, very clear book. You don't need a degree in computer science to understand it. A bit of maths, certainly, but I think the ideas in it are very clear. And then on YouTube, there's the reinforcement learning bootcamp. So I think, so just to summarize, reinforcement learning mimics the way we and other animals use trial and error to interact with the world to solve tasks. All you need is an environment and a reward signal. And of course, the reward signal is something that you as the programmer has to code in. And the agent learns the values of being in particular states, and its aim is to always move into the most valuable states, which will in the end lead it to the high reward states. From moving through the highest reward states, the highest value states, this comes a policy, and the policy is how best to maneuver through the environment. And many, many problems can be solved using this framework. So I think I'm going to stop there for now, but I'm very happy to answer any questions that you might have. Thank you.
Thank you so much, Jonathan. I'm just quickly going to make some changes here in the background.
Sure.
Right, thank you so much for addressing that, Jonathan. That was absolutely a fascinating topic. There is a lot of people in this crowd that are very much involved with IT, and a lot of people that are very much involved with programming and understand the logic and the background. And even for those that are not quite involved in those levels of expertise, I think we can absolutely see the value of things like that come in to even, with that very nice example of, self-driving vehicles. And I think that is a very, very, very practical example of how that sort of boils into our everyday life. But even, you know, when with the involvement with telescopes, and, you know, as you were saying that, an example came to mind that we had Willie Koorts from SAO on here doing a presentation for us very late last year, talking about the amount of artificial intelligence that is involved with telescopes deciding on certain objects, and, you know, how they're going to decide on what are they passing on to the next. Yeah, so I think this definitely a very practical application there. What I would like to do is open up to the rest of the audience. Guys, you're welcome to unmute yourself. Please switch on your videos if you want to, and we can ask any question to Jonathan. You can please raise your hand in the participants window so that I can know, or otherwise, you know, just fire away, please. We'll just give the guys a minute to sort themselves out.
Sure.
Just for
everybody.
Yeah, just for some background technical issue. I've been chatting in the background to some of my IT buddies, and between ISPs, we've had a DNS issue, which has resulted in some people having issues signing in. That's why the link didn't work for everyone to sign in, but they had to go through the username and password route, which is very unfortunate and bad timing. But, you know, that's what I'm saying. Thank goodness we had the alternative way of logging in. Even here in HMeet, I see some people's Adversarial is just not working. I just say, thank goodness mine is still up. All right. Is there anyone that has a question for Jonathan?
Yeah, I've got a question about Galaxy Zoo. And a little plug as well. So tomorrow's, what day are we? Oh, Friday's radio show is an interview with somebody called Ivy Wong. Oh no, I've got that wrong. Sorry, the following week, I'm interviewing a guy from the Netherlands, from the LOFAR telescope, and he's a postdoc student, and he's been setting up Radio Galaxy Zoo, and so what he's wanting to encourage, and in fact I'm going to get him to give a talk to the Cape Centre later in the year, so there's the plug. We're going to get a talk from this guy later in the year, and he's going to encourage people to become volunteers and to identify these galaxies, a bit like with normal Galaxy Zoo, but this is with Radio Galaxy Zoo. And you know, identify where there might be sort of certain sized black holes or whatever, and big radio jets. So it sounded like the task that needed to be done by the humans, which was identifying the source of these radio jets, could have been done by a computer if you program the computer. So are there just some limitations in, you know, what are those limitations? Why can't they get a computer to do this?
Sure. So generally what one needs in this case is to start off with a labeled data set. So let's say you have a catalog of 1 million galaxies. If you get humans to label some subset of them, so humans actually look at them and say, this belongs to this class and this belongs to this class. Once you have a labeled data set, you can then get a computer to label the rest of them, you know, so long as there are well-defined features. So humans are often useful in the initial labeling of your data set, and then computers take over and they can, you know, the point is that computers can do it very fast once they have figured out the rules, but they can only figure out the rules given a labeled data set in this case.
So, but why would they need so many people to do the labeling?
So I think actually the original Galaxy Zoo was done at a time that, from what I remember, using powerful convolutional neural networks wasn't actually that powerful to classify things like galaxies. It just wasn't doing a very good job. I think it's only been in the last few years that we've got to the point that they are really, really good at classifying. So neural network architectures have come a hugely long way in the last 10 years or so in terms of image recognition. And so I think when Galaxy Zoo started off as a citizen science project, I think it was the case that getting lots and lots of people to do this was an efficient way of doing it. But now that we've got a nicely labeled data set, computers can essentially take over.
Well, thank you, Ketchel. I mean, I must be honest, while you were busy doing your presentation, I've never heard about Galaxy Zoo. I had a quick Google in the background. Maybe, can you maybe just tell us a little bit more about actually exactly what it's about?
Well, actually, you could hang on to to the talk. I think I've scheduled him for April. His name is somewhere on my computer, but my computer's being absorbed by you gorgeous people at the moment. So anyway, he's going to give us a talk all about Radio Galaxy Zoo. So Galaxy Zoo, this is where volunteers, human beings, were given lots and lots of pictures of galaxies, like thousands and thousands of images of galaxies, and they had to classify them. So you had to click on the galaxy, and then from a list of possible galaxy types, choose, is this elliptical, barred, spiral, fuzzy blob, who cares, whatever it was on the list. And that was sort of the main task. With Radio Galaxy Zoo, the one that I was told about, there's probably more than one task, but the main one that this particular guy was interested in was where's the black hole, so in other words, you've got all these radio jets that are coming out like a fountain, pouring out of some origin, and the human being is better at guessing where the origin is. They can't get the computer to do this yet.
So I suppose one thing to add to that is, in terms of getting lots and lots of people to do it, the more labeled data you have, the better you can train your computer. So that getting lots of people to do it, that's why it's useful. Yeah.
Incidentally, you have to do a little with the original Galaxy Zoo, the non-radio one. You had to go through a little test to train the human up to see if you could correctly identify, what types of galaxies there were, and I failed. I consistently kept on failing the tests.
Well, that's also a neural network problem, but the point is that neural network is the one in your brain.
Ketchel, if you took the test last year March, then we would excuse you because you had a foggy brain.
Well, look, they all look like fuzzy blobs to me, these faraway galaxies.
Excellent. Thank you so much. Guys, are there any more questions for Jonathan?
Perhaps I can just step in. I hesitate to say that I've dabbled in a little bit of machine learning, for example, trying to identify genetic defects based on images of patients potentially with those congenital defects. And despite my inexperience in doing so, it proved remarkably accurate. To what extent does one's advancement into machine learning actually reveal just how intelligent we really are? A lot of this seems very basic, and yet it surpasses our capability. If you look at looking at ECGs, for example, and being able to identify certain arrhythmias with greater accuracy than a physician might be able to do. Are we learning more about ourselves rather than what the potential of machine learning might be?
So I think it's true that for very well-defined tasks, we're finding that computers can do this extremely efficiently now. And there are lots of things that they far surpass humans at. This idea of creativity, which certainly was seen in the game of Go, there still seem to be lots of areas where humans are creative that we still seem to have the upper hand. I don't know how much longer that's going to go on for. You know, you have computers which are making music and art and all sorts of things, and even writing now. I don't know if you saw this this letter to the Guardian written by a computer, it was written by a computer system called GPT-2 or 3, I don't remember which. But essentially, the rule is very simple. The computer learns that given a certain string of words, it predicts what is the next likely word in the sequence. That's all it does. And actually doing this, it was able to not only write text, but to write text about, I seem to remember it was essentially why we should fear artificial intelligence. And this was published as a letter to the Guardian. So we're sort of slowly seeing these things that certainly to our eyes seem to be creative. So I think that you're right that we're seeing more and more of the areas that we considered ourselves, you know, supreme at, slowly being chipped away. And maybe we're going to have to be more and more creative to make sure that there's really a realm for ourselves within these sorts of tasks.
Thank you so much, Paul, for that question. Anyone else have a further question that they would like to add up or add on before we wrap up the evening?
When will the machines start teaching us?
I mean, they're already teaching us. I think that's exactly what happened in the game of Go. That that it showed new types of gameplay that we'd never seen before. There are computer systems used which are actually used for teaching maths, for instance. And I don't mean sort of particularly complicated maths, but for instance, if you want to get a computer to help a child to learn maths, then there's feedback to the types of problems that the child is getting wrong and is getting right. And it then decides which are the most appropriate problems to give the child such that they can learn as quickly as possible. So in many, many ways, we are already getting computers to teach us. I think as Paul said, you know, we're designing computer systems which can pick up on, you know, it may be arrhythmias or particular defects or whatever it might be that we might not have noticed. And essentially, you know, in that sense, the computers are also teaching us. They're saying, you know, this is a particular condition that we might not have seen, we might not have picked up on. So yeah, I think they're absolutely already teaching us.
Thank you so much. We've got Graham from Durban that's got a question. Thank you, Graham. You can unmute yourself.
Yeah. I'm very much in the area of languages and language teaching. And I'm just wondering whether the reinforced learning is also a kind of scaffolding for language learning. So that what I'm trying to do is to be able to find ways that will make it easier for people to pick up the language. And I'm working very much in a South African context where there's a lot of second language learning, which isn't very good. You've probably seen that on the TV or heard people like our president coming out with some real mistakes. But we need to be able to have that because they're all second language learners and speakers. And so we need to be able to find ways of your computer program being able to do like Go in terms of learning how to deal with syntax and all of that kind of thing.
Yeah, absolutely. So I think that in a sense, things like that are already being used. So there's this website, Duolingo. I don't know if you've come across this. And that uses systems which figures out which are the words that you haven't seen recently, or the sentence structures that you make mistakes on most often, and it will then give you those as the next thing to practice. So things like spaced repetition learning and Duolingo, which use artificial intelligence within them, maybe not in very complex ways, but in a sense, as a teacher, you are always using reinforcement learning with your students, in the sense that you say, yes, you were right, or no, you were wrong. It might be more instructive than evaluative. In fact, there's some research a little while ago that said that evaluative research for certain things is actually very useful. So I think this was in terms of weightlifting. This was in terms of sports. That when a person has a clicker, the sort of clicker you would use for dog training, you can actually train sports people to perform better, rather than saying, oh, you should have moved your leg like this and your arm like this. If you just click when they do something good, it turns out that can be a positive way to use these reinforcers. I'm not saying that teachers should necessarily stop talking and just start using clickers, but it's sort of interesting the way there's this kind of feedback where we're learning from animal behavior and computer behavior, and the whole thing sort of can feed into each other in positive ways and potentially negative ways. So we have to be careful with these things.
Generally, those of us who are language teachers are trying to improve people's communication between one another, so that the meanings are clear. And I think that's something of what the need for AI is, so that the meanings move into more positive rather than the negative inferences that some people have.
Yep, absolutely. Yeah.
Thank you, Graham, so much for that question. I think what we're going to do at this stage is probably go with one last question before we wrap it up. Anyone else that would like to pose a question to Jonathan?
Yes, I would, if I may.
Yes, Christian, please go ahead.
In your opinion, how far away are we from artificial intelligence developing a general understanding of the world, of having a model of the world?
So in terms of having a model of the world, so there are already systems, in fact, there's something called a world model, precisely that, which is built within a reinforcement learning context whereby not only does the agent have some understanding of the value of states, but it's got its own internal simulation of the world. And from that, it can make inferences, and it can do planning and all sorts of things, which I think is a little bit different from what you're asking. But models of the world built into these systems is already a part of them. I think that in terms of something more general than that, something that might be termed sort of a generalized artificial intelligence, there seems to be such a debate on this, and I think that we are often tricked into anthropomorphizing these systems, perhaps beyond what they should really be. So, for instance, with these text creators, this GPT-3, these transformers, they can create text which looks, truly like it's been written by not only a human, but a human with deep knowledge and understanding and pathos, and they're incredible. But in fact, what's happening is, this is a neural network with a particularly interesting architecture, and it's just crunching the numbers. It's so difficult to know what is going to be the stage that we can say, wow, this is really something which has got a handle on the way the world works. In the same way, what's happening in our brain is really just the crunching of numbers. Those numbers happen to be the firing of neurons and the changing of synaptic weights. But essentially, we're just number crunchers in maybe an analog way rather than a digital way. So I just don't know. It could be that we have some major breakthrough in the next 3 or 4 or 5 years, or it might be that there's something fundamental that we're missing, and it's going to be many, many, many decades off. So I don't have a very good answer for you, I'm afraid. But I think it's a fascinating question.
Thanks.
Sure.
If I could just throw in one associated question, perhaps, to what extent is machine learning a slippery slope towards what we've all been warned about, general AI, or is there a chasm that divides the two? Machine learning seems to be so filled with benefits, whether it's some electronic toaster that can toast our toast better, or medical advances, et cetera. But is it the slippery slope to something that might lead to catastrophe, as Elon Musk and Bill Gates and the like have been warning us of?
So there's a field which has come up over, I mean, it's been around for quite a long time, but it's become much more important recently, about ethics in AI. And you know, the potential truly catastrophic effects that having something with some runaway behavior that we lose control of, you know, what could happen then? The point with these things, I think, is that even if we believe that it's a relatively small chance, they truly are existential threats. So it might be that, you know, you believe there's only a, you know, 0.001% chance of it happening in the next 100 years, but if it happens, it could be something truly catastrophic. So I just don't know, but I think it's something that, I know it's something that people are looking into very seriously, because the potential threats are clearly very, very large. At least I believe that the threats are potentially very large. It is one of those things where you have two large numbers, or a very large number multiplied by potentially a very small number, and I just don't know how big that product is. You know, I don't know how likely it is to happen.
Thanks.
Sure.
All right. Thank you, everyone. Thank you so much for the string of questions. Jonathan, I hope they made you think.
Absolutely, always. Thank you.
Fantastic. All right, Jonathan, I would like to take this opportunity to so much thank you for taking your time out to come and address us here at Cape Centre. Congratulations on being the first speaker of the year, only in our 3rd month. But once again, thank you so much. We really, really appreciate. And the topic was very entertaining, you know, and it's skirted along the fringes of astronomy. And, you know, I think we definitely have an idea of the wide fields of where this could be applied on. Thank you so much, and we wish you a pleasant evening.
A pleasure. Thank you very much.